I'd like to demonstrate an AutoKinetic reactor within ProMax. So the AutoKinetic reactors can be found here in their shapes grouping. I have selected this catalytic fixed bed, and we're going to use it in this simulation as a hydrotreater reactor. And so what we have going on here is we're sending a naphtha that we have that is full of different sulfur compounds, and we want to destroy those sulfur compounds, react them to become H2S, and then we can remove that H2S from our system. So you'll see that our feed has very little H2S, but a large amount of sulfur compounds, and then our reactor effluent no longer has those sulfur compounds. It has all been converted into H2S. Now the composition for our naphtha comes from this speciation block that you see here, and we'll have another video that describes how that works. But basically we've input like a TBP curve into this block, and it's created a composition for us for our naphthas that we can then use in this system. If I open up the reactor, and let's take a look here at the two streams we have coming in and then coming out, we can see that we have a very long list of components with all the different possible alkanes, cyclohexanes, aromatics, all these different sulfur compounds as well. So we have selected all these components in our environment, and then that speciation block has created this composition for us. So we just come up with the list and then it gets filled in. Now let's talk about the reactor itself. If we go to its process data tab here, we'll see the different parameters that we have to play with. Very first thing we'll need to do is choose what type of reaction set we're using. So you'll see our list here, and that list does include this hydro-treating application that we'll use it for right now. Once we've selected our reaction set, now ProMax knows what types of reactions can take place with this catalyst. And so moving on from there, we next choose whether this is an adiabatic or isothermal process. We can choose how the hydraulics and the pressure drop will be calculated, whether we want that to be user input, meaning that we just type in a pressure drop, or it can calculate a pressure drop for us based off of these two methods. Next we have our flow configuration, whether that's a downflow or upflow, etc. Our mixing regime, whether that's plug flow or a mixed flow type application. We can also account for the wetting that we have on our catalyst, so whether this is a fully dry or fully wet application, or if it will be partially wet. We also have these two different models we can use for that. The particle phase, this is the phase where the reactions are taking place. So in this case it's the vapor that will be reacting. And we can also account for some deactivation of our catalyst. I have constant activity selected, meaning that our activation will stay constant, but we can account for the steady deactivation using this second option. And if we select that, it's going to ask us for things such as our catalyst half-life, those parameters that we'll need to account for that. So those are the first basic parameters we need to input. From all this information, ProMax will calculate a pressure drop and temperature change for us, or a heat duty if this was an isothermal process and we were keeping the temperature constant. We will need to decide what our inner diameter should be. And so we have a shell diameter of 10 feet in this case. If we had a center pipe in the middle of our reactor, we could account for that as well, although we've set that to be 0, meaning that we don't have a center pipe in this application. We can also put in our catalyst mass. So depending on how much mass we have, this will help us know the extent of our reactions. And along with the catalyst mass, we need to describe what our catalyst looks like. And so we can choose the shape of our catalyst, diameter and density. We'll then have our void fraction for our particles, which will then calculate this particle density. You could input either the density or the void fraction, whichever one you have available to you. Moving on from that, we also have a particle packing fraction. And this is the exact opposite of our bed void fraction, so whichever you have there. But this is essentially taking into account how well our catalyst packs into the bed. If you have a diluent running through your system, you could account for that here. and also give its shape and density and diameter, if that's something that you're using in your application. From all this information, ProMax will calculate for us our bed length, our bed density overall, and it's going to use all this information to then calculate the extent of the different reactions that take place. The last thing we'll see here is this site density. And the site density is essentially saying, how many sites we have on our catalyst. And the default here is to put a number as 1 mole per kilogram, which would represent a fresh catalyst. If you do have an older catalyst and we're trying to model the deactivation that has taken place, this is a number we can adjust to account for any deactivation over time. But we'll leave that as the default of 1 for now. And so from these parameters, that's how ProMax was able to calculate how much reaction took place, and now we know what our reactor effluent is. Let me also show you this process detail button. This is going to give us some more information a little deeper into our catalyst or into our reactor bed. If I choose to open that, the very first tab we'll see here is some particle bed information. And this is actually the same information that we saw in the project viewer. In fact, if you want to add or remove information from the project viewer, you can right-click on any of these properties and choose whether you want to show it in the summary in the project viewer or whether you want to remove it from that project viewer. But that information will always be found here on the particle bed section. Moving to the next tab, the Kinetics tab, we have here our different kinetic parameters, and these values are defined by default, and these are very good defaults, and so if you're starting from scratch designing a new bed, these defaults will work well for you. If you have an existing bed and you're trying to match operating data, then we have another tool in ProMax called the Kinetic Calibrator that you can use to adjust these kinetic parameters in order to get a more accurate representation or a better match of your operating data. But again, these defaults will work well for your design cases. Next, we have a tab that illustrates the parameters involved with making those hydraulic calculations, so for calculating our pressure drop. We also have a settings tab. These settings have to deal with the iterating and the converging of the column. And then one that I'll point out to you is this plot integration results, which when I have this checked, it creates another tab here called the plots tab. And it's on the plots tab that we can create any type of plot that we would like to see, looking here at our catalyst bed. So if I wanted to plot the length of my bed versus the pressure, I could select those two properties and then right click and choose to create that graph. That will then create this graph for me. So this is illustrating how the pressure drops over my length. If I close the graph, we'll see that chart is now found here below, and I can right click on that and choose to then show it again later. You can have as many charts as you'd like, and you can have multiple things on the same XY plot. And so those plots can be really useful for you. Back here on the Active Set tab, we have a list of the different types of reactions that are taking place. So since we are a hydrotreater, we have these desulfurization reactions taking place. You could choose to activate or deactivate different sets if you so choose, but the default is for all of these to be selected. From there, if we move to this last tab, our Reaction Set tab, we can see here a list of all the different reactions that are taking place within our reactor bed. And so these reactions are dependent on the components that we had chosen in our environment. And we can see that this is accounting for a lot of different reactions, for almost 700 reactions taking place inside of this bed. The very last tab that I'll mention real briefly is this Numerical Performance tab. This gives us some information about the performance of the iterating of the block itself, and so if you're having difficulty converging the block, these are some numbers we can look at to give us an idea of how to better converge things. But as long as things are running fine, this is a tab you can really ignore. So that's the internals for this AutoKinetic reactor. A lot to swallow. Of course, if you ever have any questions, please let us know. We're more than willing to help. But we hope that this block can be really useful for you.